In order to solve a related rates problem, we need to take an equation which relates a number of variables and differentiate it to get an equation which relates the variable's derivatives. For example, if you have an equation like a equals s squared, which relates the area of a square to its length, we want to be able to differentiate that equation to get an equation relating a prime, the rate of change of the area, with s prime, the rate of change of the side length. In a related rates problem, every variable which is changing is a dependent variable. We treat it like a y. The independent variable in a related rates problem is always time. This means that if we take the derivative of an expression involving a variable, we have to multiply by the derivative of that variable because of the chain rule. Same reason as when we have an equation like y squared equals x squared, and we take the derivative of it. When we take the derivative of y, it's not just going to be 2y, it's going to be 2y times y prime. We have to multiply by the derivative of the variable because this y is a dependent variable. So we treat all the variables the same way we treated y's when we performed implicit differentiation. So in example 1, we're going to differentiate the equation a equals s squared to get the relationship between a prime and s prime. So we want to take the derivative of a, we get a prime. When we take the derivative of s squared, we have to remember that we're treating the s like a y. So we're going to get 2s, but then we're going to have to multiply by s prime because of the chain rule. So a prime equals 2s times s prime. We've seen how to differentiate an equation involving two variables to get a relationship between these variables' rates of change. The next step in solving a related rates problem is to use information given about one rate of change to find another rate of change. To do this, we just have to plug the given information into the equation relating the rates of change and solve for the other rate of change. Note that, in general, the equation relating two or more rates of change will also involve the variables themselves, as well as their derivatives. For example, before we had the equation a prime equals 2s times s prime. So if we want to know a prime, we need to not only know s prime, we also need to know s. So it's often necessary to know the value of the quantities themselves, as well as the rates of change in order to find the rate of change in question. Now sometimes you might not be given s. Sometimes you might be given a, for example. But because we had the original equation, a equals s squared, we could use a to find s, and then plug that s into this equation. So sometimes the original relationship between the variables is useful to find the value of one of the variables given the value of the other. So let's see some examples of this. In example 2, we have the volume and the radius of a sphere, and they're related by the equation v equals 4/3 pi r cubed. We want to find v prime if r equals 4 and r prime equals 1. So the first thing we've got to do is we've got to take this equation and differentiate it. We get v prime equals the 4/3 pi is just a constant, it's going to stay in front. The derivative of r cubed is going to be 3r squared, but because of the chain rule, we have to multiply by r prime. These three cancel, so we get 4 pi r squared times r prime. Now we're told what r is and what r prime is, so we can plug those in. 4 pi, r is 4 squared, r prime is 1. 4 squared is 16, 16 times 4 is 64, so my v prime is going to be 64 pi in this case. In example 3, we have two quantities x and y which are related by the equation xy equals 24. We want to find y prime if x prime is negative 2 and x is 6. So again, we're going to start with this equation and we're going to differentiate it. We're going to use the product rule in xy. The derivative of x is x prime, multiply that by the second, which is y, plus the derivative of the second is y prime, multiply that by the first, which is x. The derivative of 24 is 0. So now we're going to plug in the information given. We're given that x prime is negative 2 and x is 6. So we have negative 2y plus y prime times 6 equals 0. Now we still can't solve for y prime. Why? Because we don't know y. Well, we can use this original equation to find y. X is 6, so we have 6y is 24, which means that y has to be 4. Then we can take this y equals 4 and plug it in here. We have negative 2 times 4 plus 6y prime equals 0, which means that 6y prime equals 8. So y prime is 8 over 6, which can also be written as 4/3. So here my y prime, the rate of change of y, is 4/3.